Okay, so I'm Eric Phipps from Sandia Labs in Albuquerque, and this is work that we've done for several years, primarily with Roger Pulowski and Christian Trott on integrating a package that I've been developing for a long time now called Sacado, which is for automatic differentiation, and integrating that with this Cocos package, which you've probably heard about before. For Manycore parallelism and making them work together so that you can differentiate codes that use those tools. And the particular challenge that arises when we do that is getting things to work well and efficiently on GPUs. And that's what this talk is about. It's sort of an introduction to Sacado and then how we actually use it on things like GPUs and get reasonable performance. So Sacado is a package in Trilinos. It's been around for quite a while in Trilinos. I don't remember exactly when it was first put in, but it's been probably, I don't know, 15 years ago or so. And it's for computing derivatives. And I think, the importance of computing derivatives is pretty clear, especially, given the last talk where if you want to do optimization, you need things like gradients. If you're doing implicit time stepping or steady state solvers, you need Jacobian matrices. And also for things like UQ, sensitivity analysis, stability analysis, all these things require derivatives. Of course, you can always code these up by hand. That tends to be very error prone and very time consuming. It's very difficult to verify that your derivative is correct. So often people result to numerical differentiation or finite differencing, which is difficult to make accurate, and it's also can be very expensive. So I think a much better alternative is a technique called automatic differentiation, which seems to vary a lot whether people have heard of this or not. It's a way of getting an analytic derivative out of your code, like you hand coded it, without having to go through the work of actually hand coding the derivative yourself. So this is a very simple example of how it works if you've never seen it before. If you had this function here that you wanted to evaluate and then compute its derivative at x equals 2. So on the left here is a set of statements that a compiler would conceptually turn this into. This column here is the values in memory of each one of these steps. And then all automatic differentiation does, so there's different modes of automatic differentiation for computing different kinds of derivatives. This is what I'm describing here is called the forward mode, which is the simplest. And it just uses the fact that each of these statements is a simple function that has a known derivative, and then you have the chain rule in order to sort of paste derivatives together from line to line. And so you, in addition to evaluating each function, you also evaluate its derivative using known formulas from calculus. And then you have the corresponding values for the derivative of each of these intermediate quantities with respect to x at x equals 2. And then we finally get to the y, you finally have dy dx, and you get this value in memory. So it's conceptually a very simple tool or idea. The challenge with it is how do you do this efficiently in large scale scientific computing codes? And that's what the focus of this Sacado package has been from the beginning. It's designed for C++ code specifically. It uses what's called the operator overloading approach, where Sacado provides different what we call scalar types, which are classes essentially that act like regular floating point scalars like float or double, but overload all of the mathematical operations to not only compute that operation, but also compute the derivative of that operation as a side effect. And what these data types do to store that is they just have an array of data in them that stores the derivative with respect to whatever the independent variables are in your calculation. So again, conceptually, that's pretty simple. Operator overloading can be very expensive because it introduces a lot of overhead. You're basically replacing what was a single instruction with potentially an entire function call. And so there's a lot of techniques that have been developed over the years to eliminate that overhead as much as possible, and particularly this technique called expression templates, which is what Sacado uses very heavily. But the sort of one of the main challenges with scientific computing is we have typically sparsity in our codes. You know, a particular finite element code, its Jacobian matrix would be a very sparse matrix. Sacado itself is not designed to handle sparsity in any way. And instead we rely on more of a software engineering approach where, you know, typically these kinds of codes break down into some kind of loop over cells in a mesh where you do some kind of local calculation and then assemble those values into some data structure. So the way we use Sacado in these codes is we just differentiate that local calculation, which is typically a dense derivative, or can be well approximated by a dense derivative, and then manually assemble those, extract those derivative values out of Sacado, and then assemble them into a Jacobian matrix or a gradient vector, or, you know, whatever it is that you're trying to do. And that's been very successful. There's been a number of codes at Sandia and elsewhere that have used that approach. This picture on the right here is an example of computing an adjoint surface using this technique in a code called Dracar that is developed at Sandia for doing CFD and MHD type calculations. And then the subject of this talk is that we've integrated these tools with Cocos, so that if you have a code that uses Cocos for its finite element assembly or whatever calculation it's doing, then we can differentiate that thread parallel code with Sacado. And what I'll do in the remainder of the talk is describe kind of how that works. So if you're not familiar with Cocos, it's a C++ API for developing performance portable applications. It provides an API for expressing parallelism at a shared memory level, and then it has different backends that execute those operations using the architecture's sort of best thread parallel programming model. So that might be threads or OpenMP for multi-core CPUs, or CUDA or HIP or SYCL for different kinds of GPU architectures. But the point of it is that it sort of abstracts out the details of all that parallelism and makes your code portable to all these architectures by just changing out the back end of whatever architecture you need to compile for. So this is a very simple example of using Cocos that I'll use to describe how we differentiate it with Sacado. This is just computing a matrix vector product, a dense matrix vector product. So we have a 2D Cocos array here. The multi-dimensional array data structure in Cocos is called a view. You specify the number of dimensions through the number of pointers in the data type. So this is an array, a 2D array of doubles of size m by n, and then somewhere in other code you'd fill a, and then b is a vector of length n that you're going to fill somewhere, and you're going to multiply a times b and put the result in c. This code here is a very simple implementation of that in parallel, where it just does a parallel loop over the rows of the matrix A. Here I is a row, and then it just computes the matrix vector product for that particular row and stores it in C. And then the idea is that depending on the backend that you use, different threads will call this lambda function here with different values of I to compute this thing in parallel. This Cocos lambda here is just a macro that expands to a capture by value lambda conceptually, but there's additional markup in there so that it can run particularly on CUDA and HIP architectures. So it's, you know, that's fairly simple to get good performance on GPUs. In particular, Cocos does a polymorphic layout of the 2D data, in this case the matrix A. So on a CPU, each CPU thread will, it'll schedule each CPU thread to process a chunk of rows of the matrix. And then the matrix data will be laid out in a row-wise fashion. And that gives good cache-based performance for each thread, since an entire or portion of a row will come in on each cache line. Conversely, on a GPU, it will transpose the way it lays out the matrix in memory into a column-wise format, and then schedule threads so that neighboring GPU threads, here this second number here is the GPU thread within a warp, and then the first number is like a warp index. Neighboring GPU threads will process neighboring rows, and that's so that you get coalesced memory accesses, which requires that consecutive threads access consecutive values in memory. But so the two takeaways are from that the thread scheduling is different, and then the memory layout for multidimensional data is different. But using that, Cocos can achieve sort of good performance. In this case, this is, if you make M and N large enough, this should be a bandwidth limited operation. This is some performance results of running this on a Skylake architecture with OpenMP and an NVIDIA V100 GPU architecture, and showing the bandwidth that you get from running this calculation here compared to what you would well, I guess using the measured band. So what we did was we measured the memory bandwidth using something like Stream. Using that bandwidth, you can predict what the floating point throughput should be, based on the fact that you do essentially two multiplication or a multiplication and addition every after reading two doubles. So using that bandwidth, you can compute what the expected throughput would be. This is what we then measured the throughput to be on these two architectures, and you can see it matches pretty well. However, if you use the wrong memory layout, so particularly on the GPU, you use this row-wise layout, or on the CPU, you use a column-wise layout, you see that you lose all of that performance, particularly on the GPU. Okay, so that's a sort of quick introduction to Cocos and how it uses its polymorphic memory layouts and thread scheduling to achieve sort of portable performance. So what happens now if we want to try and differentiate this code using Sacado? So as I said before, Sacado provides these little classes that store derivative data. They're essentially a value and an array of some length. And there's different ones that store the data differently, and they implement the derivative calculations differently. This SFAD one is sort of a simple one to use, and it's usually pretty performant if you know the length of that derivative array at compile time. So P here would have to be some compile time constant that says I want to compute P derivatives. And then internally, it just stores a value field and then an array of length P. So if you create a 2D view of these Sacado SFAD objects, essentially what you have in memory is shown here on the CPU and the GPU. Because the data in a class is always stored contiguously, regardless of what memory layout you use for the array, whether that is what Cocos calls layout right or layout left, this data in the SFAD object will always be contiguous. And that causes problems for GPU architectures in particular, because now if each thread is processing, if two consecutive threads are processing two consecutive rows of the matrix, then the value and each derivative value that it processes as it implements its overloaded operations for computing the derivative, they're going to be separated in memory by a stride given by the derivative length. And that essentially destroys your coalesced memory accesses and then destroys performance on the GPUs. On a CPU, things still work out okay, because you'd want the derivative values to be all come in on a cache line, so you get still the right layout there. So to fix this on the GPU, there's different ways that you can go about doing this, and I'll talk about two different ways in this talk. The first approach is the simplest, and its basic premise was we don't want to change the kernels in any way. Ideally, you take exactly the same kernel that you used for your non-differentiated code, and you differentiate it with Sacado with zero changes apart from changing the scalar type to a Sacado type. And so the way to do that is you have to change how the memory is laid out when you create multi-dimensional views of Sacado data. And so there's a lot of infrastructure in Sacado to specialize the Cocos view data structures by specializing some internal classes and functions and so on that basically turn a rank R. So Cocos calls the rank the number of dimensions. It has nothing to do with numerical rank. They specify the number of dimensions as they call it the rank. If you have a rank R Cocos view, then essentially what happens is we turn that into, instead of a rank R of a view of Sacado objects, we turn that into a rank R+1 array of whatever your floating point data type is, double or float. And then whatever layout that Cocos is using, for example, layout left, we then apply that to this, this internal rank R+1 array. And so what would happen here is so in this case, we had it started with a 2D array. Now we have a 3D array of doubles with all of the derivative data in it. It would still be layout left. So that would mean the first index is the sort of contiguous index or the leftmost index. And you would still have your coalesced accesses because these values would be stored consecutively in memory. But what that means is that in Sacado's implementation of its overloaded operators, there's now a stride between consecutive derivative components in any one AD object. So we had to modify Sacado to support that. And then we have a lot of infrastructure in Sacado that specializes all these Cocos data structures for this. But using that, we can achieve sort of the performance portability that is sort of desired with Cocos. This is results of running that same kernel that I showed earlier with SFAD with a derivative dimension of 8. And again, the same experiment where we take the expected throughput, compare that to what we actually got using this Cocos specializations on the CPU and the GPU, and then compare that to if we do not use this specialization, if we just turn that off and do the normal Cocos view implementation with Sacado inside of it, you see you lose quite a bit of performance on the GPU, essentially no change on the CPU, but quite a bit of performance on the GPU, and that drop in performance increases as the derivative dimension increases because the stride is getting larger between the values that are read by consecutive threads. So you're sort of losing more and more coalesced memory accesses. All right. So that is the sort of simplest approach that we've taken with Sacado. It's been pretty successful in enabling differentiation of thread parallel codes, and a number of codes at Sandia and elsewhere use that. But there are more opportunities that can be taken advantage of here, particularly in the case where you have a large number of derivatives you're propagating. So you have a big multiphysics problem with a lot of coupled PDEs. So you have a lot of variables you want to differentiate with respect to. That means that the derivative calculation itself has some opportunities for parallelism. And it may be difficult for the architect, for your code to take advantage of all of the parallelism in just the application itself. So for example, a lot of our PDE codes here at Sandia use a work set based approach where you group cells into batches called a work set. and then you do your thread parallelism over just the cells in that work set as opposed to the entire mesh. So for GPUs, you'd want very large work sets because you have a lot of concurrency available in the architecture. So you'd want a large, since you typically do your thread parallelism over the cells in a work set, you'd want to have a very large work set size. But typically the memory required for that is proportional to the size of the work set. And typically these GPUs have kind of small memory. So that would mean you'd want to have a smaller work set. So what we found in several cases on CUDA GPUs in particular, was we could not make the work set large enough to sort of fully capture all of the parallelism available on the GPU. So a solution was to try and apply some of the fine-grained parallelism, in particular the parallelism within a warp, across the derivative dimension. And the way we do that is behind the scenes, we essentially have thread parallel loops using CUDA and HIP type syntax that inside the Sacado overloaded operators to take advantage of that. I don't want to spend a huge amount of time going into detail on how it works. It's kind of complicated to implement. Unlike the previous approach, which required 0 changes for the kernel in order to make it work, this approach actually requires quite a few changes. And to just sort of demonstrate that, this is an example of a PDE type kernel. This is a kernel that you might have for an advection type operation. It's implemented here for just doing the residual evaluation. This is then showing the time per cell of differentiating this code with Sacado using the prior approach that I described earlier. And you see it's displaying the time for computing a derivative per cell. So that goes down as the work set size increases using this flat parallelism approach that I described earlier. But if we use this hierarchical parallelism that I just described, we can essentially get the same time regardless of the work set size by using some of the parallelism inside the Sacado overloaded operators. These in red is all the changes in the kernel that had to be made in order to do this. We have to use a different view specialization so that on the GPU, the data is laid out differently. There's issues with if you have temporary variables, mapping the right derivative dimension across threads becomes a problem. That's what this local scalar type becomes. You have to go to a team type policy. You have to be careful to not use vector parallelism in the kernel itself. So there's a lot of challenges with using it effectively, but it can be quite a bit more performant. Another package in Trilinos is called Panzer. It's used for constructing a lot of PDE codes. It provides discretizations and so on. And in particular, it's used by this Drakkar code. And this is just some results of comparing the hierarchical and sort of flat parallelism on a couple different kernels that arise in solving a simple diffusion problem using a mixed finite element discretization. These are the different kernels that arise in that. These are sort of the names of them. This is then showing the speed up of this hierarchical approach for computing the Jacobian that's used for implicit time stepping, comparing this hierarchical approach compared to the prior sort of flat parallelism approach that where we don't use any derivative parallelism within Sacado. And you can see for the small work set sizes that are typically required to get things to fit in memory, particularly if you have things like, multi-grid operators and so on that also have to fit into GPU memory, you can see quite a bit improved performance in terms of the Jacobian assembly time. Okay, so that's sort of a description of how we integrate Sacado with Cocos for efficient differentiation of thread parallel codes. Like I said, there's two ways to go about doing it. There's this sort of polymorphism approach that doesn't require any changes to your code. And then there's this hierarchical approach where we try and use some parallelism within the derivative calculation itself. It's been used in a number of projects at Sandia. These are some well-known cases, but there's quite a few codes, especially here at Sandia, that use this. Some work that is going on, or we hope to work on. So there has been some work on higher derivatives recently for computing, say, second derivatives used for Hessian vector products. And one thing we're really keen on doing, we hope to get a chance to do sometime in the near future, is to apply these same techniques using reverse mode AD, which is a different way of computing derivatives with automatic differentiation that's particularly relevant for gradient computation, where you want to differentiate scalar valued quantities with respect to large numbers of variables, particularly for optimization. So that's all I had. Thank you.